Hello, everyone. My name is Xindong. I'm an associate professor on robotics at the Rolls-Royce University Technology Center at the University of Nottingham. Welcome to our live lab show. So here, our research focuses on the development of snake robots for helping inspection and maintenance operations in industry environment, such as aero engine, aircraft wing, telecom tunnels, and nuclear facilities. Very similar to keyhole surgery of human being, snake robots can be used to reach the defects in industry environments through very tiny access and then repair them. So in this way, there's no need of disassemble the industry environment and put them together later. So it can largely reduce the repair time and cost. We have involved in this area for more than 10 years, which is a very long journey. Today, we are going to present you three different snake robots developed in our lab. The first one is at my back. So this is the grandfather snake robot in our lab. So this robot consists of multiple sections, which is driven by cables and powered by the motors at the base. In the center of the snake, there is a flexible backbone. And by pulling the cables, those backbone can be bended into different shapes. So it can help the snake get into confined space. This robot was built for evaluating the concept and learn what is the challenge behind it. Then we developed a much better version of snake robot, and my colleague Khalid will introduce about it.
Hello, everyone. My name is Khalid Muhammad. I'm assistant professor in mechatronics at Rolls-Royce University Technology Center. As everyone mentioned, we are learning from the different demos and different prototypes we are developing here at UTC. So one main issue with the previous version of the snake-like robot that it can be easily twisted around itself because it includes a central backbone. So we overcome this issue by using twin backbone here in this version of the snake-like robot. So we have achieved the robustness in the twisting, so it cannot be twisted around itself. So it can hold like a larger payload, and also it can allow different application, for example, machining with high payload. So one main advantage of the snake-like robot we develop here is it includes a central working channel here of around 7 millimeters. So through this working channel, so we can send any kind of inspection tool or machining tools. So the basic construction of any snake-like robot is the actuation and the body of the snake. The actuation mainly include all of the motors, controllers, sensors, which normally drag and release the cables. And then the cables control the body of the snake. So we call this part here is a section, and this include a 2 degrees of freedom. And by dragging and releasing the cables, we can control its bendability. So one advantage also of this snake is that it can be coiled around itself, so it becomes a very, very compact. So instead of using this space, it just uses the space of the actuation back. And once it becomes very compact, we can send it easily to the intervention location. And after that, we have developed a control algorithm for it to be uncoiled and then navigate inside a confined space. So as you can see in the video here, so we have demonstrated this one in a nuclear environment. So you can see now the robot is coiled and then start to uncoil and navigate inside this pipe to do inspection or repair. So the robot itself is very flexible. So you can navigate inside confined space or avoid any obstacles in the working environment of the snake. Also, we have demonstrated this one in a glove box, which is a part of nuclear facilities, where you can see here the robot is uncoiled and then navigate in a very tiny hole inside this glove box. And it can reach a very difficult to reach location, which cannot be accessed by the conventional industrial robots. So this is one version of the snake-like robot. It's very long. Also, we have a very short snake-like robot here, so which is a couple of centimeters. And also it's controlled by cables through this actuation back. At the tip here, we have a grinding tool, which can do machining in a confined space. And this project, we have developed it with Rolls-Royce. And the main idea of this one is to attach it to the engine. And after that, a person who is working remotely can control this robot, for example, from Derby. So if you look to the size of this snake, the diameter is around 35 millimeter, which is not appropriate for all of the application of the engine inspection. So after that, we have developed a smaller version, which is just 12 millimeter. And I'm passing it to Erwin to introduce next version of snake-like robot, which is Flare.
Hello, everyone. So we are going to show you a video of the Flare system. So in this system, there is a pair of snake robots which can enter Aero engine through a very tiny inspection hole for thermal barrier coating repair in Aero engine combustors. So from this video, what you can see is two snake robots working together, and one snake robot is taking care of the inspection, and the other one take care of the repair. And now what we are seeing is the repair snake doing a mock-up pass run before it switch on the flame. And here, what you are seeing is the inspection snake ignite the flame from the repair snake. Bear in mind, the flame here is nearly 3000 degrees C. So the inspection snake needs to move to a safe zone. And then it can turn the camera to the flame and monitoring the operation of the repair snake. And after the multiple process of repair, the inspection snake will do a check on the repair surface. If everything is fine, two of the snake will retreat from the tiny inspection hole. So far, what we have presented you, all the snakes are around 1 meter long, and the arm is directly attached to the actuation system. So in this way, the robot needs a large transport box, which is not very friendly to the end users. Recently, we developed a much longer snake, and it is modular, so it is user-friendly for the deployment. So next, I'm going to hand it over to Sam to introduce our latest development.
Hi, everyone. Student here at the University of Nottingham, and I focus on the control of the Cobra system. So what you've seen is robots with rigid backbones. The difference with this robot is we have a long, flexible backbone, and then an active section in which we can control. So each individual active section is made up of vertebrae, and these vertebrae are spaced with Nitinol rods, and we can pull on a cable, and we can bend each individual active section at a time. So this is the Trent 900 turbine. Normally, we will go inside of this turbine and actually use a camera and inspect the inside of it. This is done by boroscopes. So boroscopes are long, flexible devices in which we have to push and feed into the system. We have now created a robot that can feed itself into the system itself. So this here is the actuation pack. It consists of a modular base for the robot, and all of your cables are along here. They are also linked to 12 individual motors. Now, so 4 of these motors will control one active section at a time. So we have 3 sections on this robot. Here we have the long flexible backbone, which is made up of 12 cable guides, which is really flexible. We don't have control over this section. And then inside of the engine, just up here, is the robot itself. So this is made up of the individual vertebrae I talked about, and then we also have a camera at the tip to perform inspection. So I'm now going to control the tip of the robot, so you can see it moving up and down, so the boroscope engineer can inspect just using this robot. We also have there you go. We also have a mechanism in which we can move the robot up and down. This is the twist and feed mechanism. So we can move up and down the turbine to inspect. And this is when we can twist. The controls are exactly the same as the boroscope engineer will use. It is a joystick moving up and down to insert the robot, and we can select an individual section and move it around just by using this thumb. So it's a really easy method of controlling the robot. I'm now going to pass over to Muhammad, who is going to talk to you about another industrial application of our robots.
Hello, everyone. My name is Muhammad Al-Banna. I'm a PhD student here at the University of Nottingham. And one of the projects that we want to expand Snake Robots to is inspecting the infrastructure, specifically the telecom infrastructure. So BT, they have ducts all around the ground, full with cables that carry the internet signal, telephone, and all of that. And usually what they do is they insert what you can see here, the orange rod, to see what's inside the cable, but sometimes it's difficult to navigate between the cables. So our idea is to add a Snake Robot at the tip of the orange rod that would allow us to navigate in between the cables so that we have a better inspecting technique for this underground infrastructure. And that's all. I'm back with Khalid. Thank you.
Thank you, Mohammed, for presenting the last bit of our industrial application. And thank you also for all our audience for, and I hope you enjoyed this show. And we are happy to take all of your questions. And before ending the session, I would like to thank all of our team here who demonstrated this demo. If you can turn the camera for everyone. So we are happy now to take all of your questions, guys. Thank you. Thank you. So here I have a question. Is it possible to merge the mechanical actuation joystick with the other robot? So the mechanical actuation, the one which we developed for BT. Yeah, actually, this is a nice question. We have demonstrated also this mechanical joystick in a medical application where the doctor used this mechanical joystick in order to control a couple of a very small snake-like robot at the tip of Cobra in order to do cancer treatment in the throat. I hope this answered your question. So do you like to?
Yes. Next question. Could these snakes be used underwater? Yes. Well, but the advantage of those snake robots we developed is in the snake body there is no mechatronic system, or there is well, very little mechatronic system, so they can be used for underwater applications. For example, nuclear pumps, we can send this snake, well, the arm of the snake into the water and do inspections. So compared with other robots used for underwater, snake has a lot of advantages. For example, underwater robots, there are propellers, so it can get the dust from the underwater mixed with water, and it will lower the visibility in the water. But our snake robot can go into the water, and there is no. It will not introduce turbulence into the water, so it can keep the water clean. So it's very good for inspection. How to evaluate which is benchmark? Okay, I think this Khalid, you could answer this one. We just discussed it. Yeah.
This is a question, how to evaluate the control performance, which is a benchmark problem, please. So, okay, so control performance, it will depend mainly on the application. So, for example, if you would like to do a time-dependent process, the one similar to the thermal coating application. So, in this case, we need to make sure that the robot all the time follows the desired path accurately in order to achieve a homogeneous thermal coating, for example. So, in this case, the evaluation will be how the robot will follow this particular path and how much error will the robot or the tip will deviate in both in position and orientation. But some other application also, we need to do an inspection of point-to-point movement. So I need to go inside the engine to a particular point, and then I need to apply a particular force or a particular position accuracy in order to take the measurement. So in this case, we are going to evaluate the robot on point-based accuracy.
I can also answer from my perspective. So in my PhD, I need to develop the control algorithm and also evaluate it. So from my perspective, I need to actually get this robot to be perpendicular to the turbine surface and to move point to point, as Khalid addressed, and also another shape, so like a circle or a square or a spiral for a specific machining process. The way in which we actually feed back this information to us, like we currently don't have any sensors inside of this robot, so we need to use another method. So we actually have like 4 additional cameras, which we can place reflective markers on the tip of the robot and at the end of each section. So from there, we can feed back the position of the active tip, and then also evaluate where the tip is moving.
Yeah. Thank you. Is it the time? So we are happy to have
My name is Shindong. I'm an associate professor on robotics working at the Rolls-Royce University Technology Center at the University of Nottingham. Welcome to our live lab show. So our research focuses on the development of snake robots for helping the inspection and maintenance in industry environment. For example, air engine, aircraft wing, telecom tunnels, and nuclear facilities. Very similar to the keyhole surgery of human being, snake robots can be used to reach the defects in industry environment through very tiny access and then repair them. The benefit of using snake robot is it can do the inspection and repair without disassemble and assemble the facility. So in this way, it can largely reduce the repair time and cost. We have developed the snake robots for more than 10 years. This is a very long journey. Today, we are going to present 5 snake robots developed in our group. And the first one is the grandfather snake robots we developed about 11 years ago in a EU-funded project. So in this robot, there are multiple sections actuated by steel cables. And those steel cables connected to the motors in the base of the snake. So the snake can have a very small diameter and a very long length. In the center of the snake, there is a flexible backbone. By pulling those cables, those flexible backbone can be bended, and in this way, the snake robot can get into very narrow and confined space. So we built this grandfather snake for evaluating the performance of this concept and also to find out what are the challenges at the behind. After that, we developed a new version of snake robots, which has much better performance. And I'm going to hand it over to my colleague, Khalid, to introduce about the other robots.
Thank you, everyone. My name is Khalid Muhammad. I'm an assistant professor in mechatronics at Rolls-Royce University Technology Center. As everyone mentioned, so we have a very long journey in the snake-like robot development. And here I'm going to show you the second generation of the snake-like robot. And in this second generation, basically, we avoided all of the issues we found in the first generation. And the main issue with the first generation, it was easily to be twisted around it itself because it depends on a central backbone. And this doesn't give the, like the rigidity for the snake-like robots, so they cannot be used for high-duty application, for example, machining or carrying a heavy end effector. So we improved the mechanical design by using different backbone, twin backbone here, as you can see. And this allows the robot to be rigid in the twisting, so it cannot be twisted around it itself. And now it can hold like a larger payload, and it can hold a larger end effector. The main construction of any snake-like robot is basically 2 main components. The first component is the snake itself, which consists of several sections. So this part here, we call it a section. And this section is derived by 3 cables. So if you change the configuration of these 3 cables, you can bend the, this section in 2 degrees of freedom. So by manipulating all of the cables, so you can have different configuration of the body of the snake. So it can navigate in a very confined space in order to do inspection and repair of different infrastructure. The second part, which is here, we call it the actuation back. So this part include all of the motors, the controllers, the sensors, and all of the electronics inside it. So it becomes very, very compact. And what we need is just a couple of cables. One is connected to the computer, and the second one is connected to the power supply. Also, this robot has advantage that it can be coiled around itself. So if we coil it around itself, it becomes very compact, and after that, it can be carried easily to confined space in order to do inspection and repair. So in total, its weight is around 7 kilograms, so it can be easily carried by a single person to the intervention location. So once it is at the intervention location, so it starts to uncoil itself and navigate inside a confined space. So any snake-like robot we develop here normally include a working channel, as you can see here. So this working channel include it's around 7 millimeter, so we can send any kind of inspection or machining tools. So here we have demonstrated this snake-like robot in different scenario. In this video, we have demonstrated it in a nuclear-like scenario. So you can see the robot is uncoiled and navigate inside a confined space, in this case, this pipe, in order to do inspection and repair inside it. So as you can see, it is very flexible compared to any existing industrial robot. It can navigate into a very confined space, avoid any kind of obstacle if it happens in the working environment. Also, we have demonstrated a snake-like robot in another nuclear environment, which is the glove box. So you have a very tiny hole, and then you cannot insert like the large industrial robot inside this tiny hole in order to do inspection in confined space in the glove box. So the solution was using this snake-like robot. So you can see it can go to a very, very tiny spaces inside the glove box. We have demonstrated it with different kind of sensors. So this one you can see here, we use the Raman sensor attached at the tip of the snake in order to detect the different material. So this part also is navigation inside the glove box, where you can navigate inside a very small tube and check what is inside it. So as you can see, this is a very long snake-like robot. It is above 1 meter. Also here we have another kind of snake-like robot, which is just a few centimeters length. And also it is driven by cables. By this linear actuator includes some force sensor also in order to measure the force at the tip. And at the end here, we have a grinding tool, which can use to grind inside the engine. So the main advantage of this one is that it can be controlled remotely. For example, you can insert this one against any engine, and then someone in Derby can control the robot over the internet and take the measurement of the machine part. So the diameter of this snake-like robot is around 35 millimeter, and the end is here around 12 millimeter, which is not appropriate an inspection task in the Aero engine. So that we have developed a more smaller version, which is around 12 millimeter diameter, and which is flare. And I'm going to pass it back to Erwin, who will introduce flare project.
All right, thank you, Khalid. Khalid introduced the one long snake robot, which is 30 millimeter in diameter. And now I'm going to show you another robotic system we developed here, which has 12 millimeter in diameter. And in this system, we have a pair of snake, which can get into Aero engine combustor through different inspection hole for repairing thermal barrier coatings. So what you see here now is the first snake, which is an inspection snake, which carries cameras into the combustor for checking where is the defects and evaluate the size of the defect. So then we can make a decision how to repair and when we need to repair. Once we decide we need to do the repair of these defects, we can send another repair snake, which carries high temperature flame tool. And now what you see is the repair snake doing a mock-up run. So before we switch on the high temperature flame, we need to make sure the path is correct and everything is fine. So now what you see is the inspection snake help the repair snake to ignite the flame. The flame here is nearly 3000 degrees C. And then the inspection snake need to retreat to a safe zone. And after it reaches the safe zone, the inspection snake will turn the camera towards to the flame and monitoring the operation of the repair snake. And after the repair, the inspection snake will do a check on the repaired surface to understand what is the quality of this repair and decide whether we need a further repair or the repair is completed. And with the support of the inspection snake, the repair snake can retreat from the inspection hole. And then the inspection snake can also retreat from the combustor. So far, what we presented, all the snakes are around 1 meter long, and the arm of those snakes are directly connected to its actuation system. So in this way, the snake needs, well, the robot needs a large box for transportation, which is not very friendly to the end users. And recently, we developed a much longer and modular snake, which can be easily transported and developed. Okay, next I'm going to hand over to Sam for introduce our latest development.
Thank you, Owen. So my name is Sam Wild. I am a PhD student here at the University of Nottingham, and I'm studying, I'm focusing on the control of these continuum robots. The one I'm focusing on is Cobra. So Cobra is different to these rigid backbone manipulators. We needed to extend the length of the robot. So the best possible way was to integrate a flexible backbone. So this flexible backbone consists of 12 springs, and then we will feed it all the way up inside of this environment. And then we will then have the rigid backbone part at the end of the robot. This is an example of the backbone, as the others have described. So it's composed of vertebrae, which are these silver pieces. And then in between the vertebrae, we have a shape memory alloy, which will return to the straight position. So we will pull on a single cable, and we can bend the robot in 2 degrees of freedom, or 4 directions. So for our robot, well, the one that I'll be showcasing here, we have 3 of these sections together, which are all stacked on top of each other and twisted by about 30 degrees. So we have about 6 degrees of freedom in which we can reach. So traditionally, inspection and repair on the engines is done by borescopes, which are long, flexible, like optical devices with a camera at the end. And they're quite difficult to control. It requires a highly trained engineer to be able to go inside of the turbine. This is the turbine. To go inside of the turbine and look around. They will traditionally feed it through with their hands and move it around. And there's like limited control. So this system, Cobra, is meant to be a solution to these problems. So coming over to the actuation pack, this box here is the actuation pack. It consists of a modular base for the robot, and then 12 individual cables. As I mentioned before, 4 of these cables will control 1 section each. This base is modular, so it can be put in and out at any case. So it's very suitable for remote operations when we need to transport the robot around. And then these are the 12 motors which will pull on all of the cables. As you can see on this screen here, this screen tells you when the robot is on, how to tighten up all the cables. It also tells you the angle of the active section so that we know which direction we're moving. It is controlled by this joystick here, which all the borescope engineers have been trained on. It's very, very similar to how they have been trained. We will move a twist and feed mechanism up and down, and then we can control the robot with our thumb here. So now the twist and feed mechanism over here is quite an interesting concept. I mentioned before, these borescope engineers need to push the robot through of the turbine. This mechanism will actually do it for you. We'll be able to move the robot up and down inside of this environment just by moving this joystick. And the speed is controllable as well. Look, I can slow it down. And here we go. Here's a bit of the twisting mechanism. So by twisting it, I can just look around with this robot and move the camera to a position that I want. Now, in order to move the tip of the robot, I can press buttons on here. These buttons will control each individual section itself. So I've just pressed the middle section, and I'm going to move it just downwards. So I'm scanning the environment, and I'm looking for possible areas in which need to be repaired. So it's really, really easy to control, much easier than these traditional borescopes. And the end effector on this robot is a camera. Now we can put multiple end effectors on here. We can do different inspection and repair operations with them. So that is the Cobra system. I'm going to pass you over now to Muhammad, who is going to talk about another industrial application.
Hi, my name is Muhammad Al-Banna. I'm a PhD student here at the University of Nottingham, and I'm working on how can we adapt this snake robots technology and use it in inspecting the infrastructure. So supposedly, the infrastructure is full of ducts that has many cables that usually carry the signals of internet, telecom, everywhere. And the traditional way of inspecting it is using the orange cable that you see here on the slides, and push it manually, try to push it between the cables to see if there's any damage in the cable. So what we're trying to do is to attach a snake robot at the tip of the orange guide and then control it so that we can navigate easily between the cables. To test the idea first, we created a mechanical joystick that can control the snake robot that's attached to the tip of the orange rod. And as you can see here, we have tested it in order to make it maneuver between cables and then push it so that we can guide it between cables without damaging the cables and have better view of what's inside. The challenging part will be how can we extend this snake robot to reach a distance of up to 50 meters. That's all for me. I'm back with Khalid. Thank you.
Muhammad. So as you can see here, we are like working on snake-like robot for different application in aerospace, nuclear, telecommunication, and recently we have developed several like different design, different control strategy for all of them, and we still continue working on this kind of activities. Also, we recently expand the application of snake-like robot from industrial to medical application, but in today's demo, we focus only on the industrial application. Thank you very much for your attention, and we are very happy to have any question from you. And before I end this session, I would like to thank all of the guys who contribute to this demo. So ask any question, guys. We are happy to answer them. Okay, so here I have question. So what is the relationship between the length of the robot and its position accuracy? Can you perform accurate repair operation? So this is a very good question. So we start from this very short robot. Because it is very short, we can achieve a very high accuracy. So if we extend the robot length, probably we are going to lose some kind of accuracy. But also we have developed some solution in order to avoid this problem. So one of this problem is to attach a fixture at the tip of the robot. So you don't care about the length of the robot, regardless of the length. You fixture only the tip of the robot, and then you can start to achieve more kind of accuracy. So one example of this fixture is using balloon, for example. So once you are at the intervention location, you can lock the tip of the robot, and then you can achieve more accurate option.
All right. Next question. Can we apply haptic sensors feedback at the tip of the snake robot and send back to the user? Okay, so very good question. Sensing of snake robot is very important to the end users. Shape sensing, force sensing, those information can give the operator of the snake robot a better understanding what the snake is hitting or contacting in the industrial environment. So haptic sensor is definitely is possible to be integrated into snake robots. For example, we can use very tiny piezoelectric sensor in the tip of the snake to measure what is the external force or torque applied to the snake tip. And then we can use this force information to do a haptic control. And also in terms of sensing, shape sensing is very important. So imagine you have a 5-meter long snake, and when you navigate the snake in a closed environment, you just can see what is in the front of the snake. So you don't have a very good understanding of what is the shape. So shape sensing is very important for snake robot. So it can help us to build a digital twin of the snake robot when it is in industry environment. So it will help the operator to have better operation during the intervention. I hope I answered your question. Next, Sam, would you like to answer this question about the navigation?
Yeah. So the next question is how to navigate the robot inside of the Aero engine. So this is a turbine of an Aero engine. All of these are like common maintenance problems. So all of these engines have particular ports on the side of them. The sides of the engine casing lift up like butterfly wings, and then we can access the internal, such as this turbine, and they'll have borescope ports. So our robot is actually designed to be the exact same diameter as these borescopes so that we can feed it in. But now you're thinking, it's blind. We can't actually see what's inside of the engine. That's why we have the camera and the light. The light is on because it's going to be a dark environment, and they will use the camera to move around and look where they're going. And as Erwin mentioned, shape sensing and haptic feedback are really common sensors that we're going to employ inside of these robots to help us navigate.
Okay. So we have question here. Could this snake be used in non-industrial or hard-to-reach environment in medicines? Yes, as I mentioned in the end of the demos, that we have already expanded the application of snake-like robot in order to do or in order to use them in a medical application. So recently we have proved the concept of using Cobra in a throat cancer treatment. We converted into kind of medical Cobra. And this is done by attaching a couple of end effector at the tip of Cobra. And these two end effector, one is holding a cutter and the other one is holding a tweezer, basically to hold the tissue and the cutter to cut the cancer tissue. We have demonstrated this one in lab, and we are taking this medical Cobra in a next stage, which is a cadaveric test. So, Erwin, do you like to take this question?
Right. What is the practical length its construction can reach? Okay. Well, actually, this is a question we are often asked in different events. So basically, the practical length of snake robot. It depends on also the diameter of the robot. So basically, for example, we have 1.2 meter long snake, and it has 30 millimeter in diameter. We also build a 7-meter long snake, which also has 30 millimeter in diameter. So the larger the diameter is, the longer the snake can be. And because we have a solution which use inflatable soft mechanism to support the head of the snake for operation. So in theory, there is no limit to the length of the snake. And the next step, we are going to build an even longer snake robot for industry applications. And now our limit is, well, our record is 8-meter long.
So yeah, in order to complement Erwin's answer as well. So as Mohammed mentioned, we are working with British Telecommunication, and they are looking for snake-like robot solution, but they are not looking for 5 or 10 meter. So they are looking for 50 meter snake-like robot. So we have the solution for this, but maybe because the work is under publication, so we cannot give more information about it. But we have the solution to reach 50-meter snake-like robot. Last question before the break. Any question? No? Okay, thank you very much, you guys. And we are going to see you after the break.
Hello, everyone. My name is Shindong. I'm an associate professor on robotics working at the Rolls-Royce University Technology Center at the University of Nottingham. So welcome to our lab show today. So our research at the UTC focuses on the development of snake robots for helping the inspection and maintenance in industry environments, like air engine, aircraft wing, telecom tunnels, and nuclear facilities. Very similar to keyhole surgery, snake robots we developed can be used to reach the defects in industry environments through very tiny inspection holes and then repair them. In this way, there's no disassembly of the industry environment needed, and also there's no need to put all parts back together. So it can largely reduce the repair time and cost. We have developed a different snake, and we started this research about 10 years ago, so which is a very long journey. So today we are going to present 5 different snake robots developed in our lab. And the first one is the grandfather snake robots we developed in a EU-funded project about 11 years ago. So this robot consists of multiple sections, and each of the sections are actuated by 4 cables, and those cables are actuated by the motors in the base of the snake. Because the arm of the snake robot is remotely controlled by cables, so the diameter of the arm can be designed really very small and slant. So it can be used for inspection and repair in confined space. So this grandfather snake robots, we built it for evaluate the concept and also find the challenge behind the concept. And after that, we build a new version of snake robots, which will be introduced by my colleague, Khalid.
Okay, thank you, everyone. My name is Khalid Muhammad. I'm assistant professor in mechatronics at Rolls-Royce University Technology Center. And as everyone mentioned, we have a long journey in learning and developing snake-like robots. And every time we learn and improve the challenges of the previous version. So the main challenge with the grandfather snake-like robot, it was the twisting, because it has a central backbone, so it can be easily twisted around itself. And this prevents this snake-like robot of holding a large payload. Basically, it cannot do a machining in a confined space with a very basic payload. So in order to improve the design, we came with this solution, which is, as you can see here, consists of, instead of a single backbone, it includes of a twin backbone here. And the main construction of any snake-like robot consists of 2 main parts. The first one is a snake body, and the second part is actuation back. So the snake body consists of different sections. So each section is driven by 3 cables in this case, and by manipulating these 3 cables, you can bend the single section in different direction, so you can have a flexible movement of the snake. And then if you have several sections, you can have the ability to navigate in a very confined spaces. So as I mentioned, each section is driven by 3 cables, and here we have 8 sections. So in total, we have 24 cables going to the actuation back, where we have 24 motor to control this section individually and simultaneously in the same time. So also we have all of the controller, all of the sensor, all of the electronics, so that everything is compact in this actuation back. What we need to connect is just a cable for the computer and the cable for the power. Also, we have additional motor here, which allows this robot to be rotated around itself. And this rotation will allow another advantage of this snake-like robot, which it is ability to be coiled around itself. So the advantage of having it to be coiled is that it becomes very, very compact. So we can send it to a confined space in order to do repair and inspection. So once it is at the intervention location, the robot, we have developed the algorithm for it in order to uncoil itself and navigate inside this confined space. So all of the snake-like robot also include a working channel, as you can see here. So this working channel is 7 millimeter, and it goes through all of the robot body and also the actuation back. So we can insert any kind of inspection tool or machining tool. So we have demonstrated this one in several environments, as you can see in this video. So we have demonstrated this robot in a nuclear environment. So yeah, as you can see in this video here, the robot first was coiled around itself and then start to uncoil and navigate inside this confined space, which in this case, this tube here. And you can see here the working channel of the snake-like robot. So you can see it is very flexible. It can navigate in a very confined space, and it is not similar to any kind of industrial robot which cannot do this kind of job. So it can avoid any kind of obstacles inside the working environment. So we have demonstrated it in several nuclear environments. This is another example where we demonstrated it in a glove box. So you have a very tiny hole where you need to navigate inside this glove box in order to find a location which cannot be reached by the conventional industrial robot. As you can see here, we can navigate to this difficult to reach location. Also, we have demonstrated it with different kind of sensors. So in this demonstration, we did it with a Raman sensor. So it can go to a different confined space, and then by using the sensor, we can identify what type of material inside the glove box, for example. So this is one type of snake-like robot, which is a very long, as you can see. Also, we have developed other type of snake-like robot, which is very short. On the other hand, which is can achieve more accurate positioning of the tip. So this project, we developed this snake-like robot of few centimeters, and also it is driven by cables with the linear motors. And at the tip here, we have a machining tool, which is basically a grinding tool. So the main advantage of this robot that it can be attached to an engine, and then it can be controlled remotely from Derby. So it reduces the maintenance time, and for example, Rolls-Royce does not need to send any specialized engineer from Derby to the location of the intervention. So the diameter of this snake-like robot is 35 millimeter here, and in this to 12 millimeter here. And this is not appropriate for all of the holes inside the engine. So after that, we have developed another version of snake-like robot, which is 12 millimeter diameter, and it can carry higher loads. And Erwin will present this flare snake-like robot.
All right. Thank you, Khalid. So the next robot I'm going to presenting has a pair of snake robots in this system. So the diameter of this snake is 12 millimeter, and in the center there is also a working channel which we can put cameras and repair tools through this tiny working channel. And the purpose of this robot is to repair thermal barrier coatings through small inspection holes in aero engine combustor. What you are seeing here now is the first snake, which is an inspection snake navigating into the combustor for checking where is the defects in the engine. So at the tip of this snake, there are cameras and also ignition tools, which will help the other repair snake for igniting the flame. And now this is the repair snake, which is guided by the inspection snake into the combustor. And after it reaches the defect area, the inspection snake will help the repair snake to adjust its orientation and position against the defects. And then the repair snake will run a mock-up pass to make sure all the control is correct. And then the inspection snake will help to ignite the flame from the repair snake. And the flame here is nearly 3000 degrees C. So once the flame is switched on, there will be a high temperature zone. So the inspection snake needs to move to a safe zone, because inside of the inspection snake, there are cameras and also other fragile mechatronics system. And then the inspection snake will monitor the operation of the repair snake. And after several rounds of repair, the inspection snake will do a check of the repair quality. And then two of the snake will retreat through the inspection holes. So far what we presented are the snake robots, which has around 1 millimeter length. And also the arms are directly attached to their actuation system. So in this way, the robot needs a large transport box, which is not very friendly to the end users. And recently, we developed a much longer snake, and it is modular, so it is much easier for its own deployment. So now I'm going to hand over to Sam to introduce our latest development.
Hi, I'm Sam. I'm a PhD student here at the University of Nottingham, and I'm working on the control of the continuum robots that we design. So the continuum robots, they're used for inspection and repair. Now, traditionally, we will have highly trained engineers to use something called a borescope to feed inside of the turbine to perform this inspection. These are basically long, flexible optic devices which have a camera at the end, and we have no control over the end of this section. So one of the robots that we've created here is called Cobra. And now Cobra is a long, flexible backbone that we don't have control over, but the end effector has different active sections in which we can control. This is an example of the active section. As you've seen on the other robots, it's a very, very similar design. So we have a series of vertebrae all stacked up on top of each other. And then between these vertebrae, we have a material which is nitinol, which keeps the rigidity. But we can pull on one of these cables and bend it. So we can bend it in 2 degrees of freedom or 4 directions. So our robot here is made up of 3 of these individual sections. I'm going to take you over to the actual system itself. So how do we control this robot? How do we pull on these cables? We actually have a modular base here in which we can bring and put inside of this computer. It will pull, it has spools that wrap around all the cables, and then it will also have motors on the side which will do the pulling of the cables for us. So 4 of these motors will control 1 active section. So we need 12 motors. But look how compact it is, look how small it is, and we can transport this box wherever we need to. The control system here is very similar to what the highly trained borescope, highly trained engineers will be using. We can understand the direction of the tip, so the tip, the middle, and the base section, and we can also check status of the system. The robot here is controlled by a joystick. It should be a similar communication protocol for the engineers to use this joystick. They use it, something very similar to control the borescope. I can move this stick up and down, and it will move something that we've designed called a twist and feed mechanism. You can see it here, just twisting at the bottom. There we go. So if I want to move my camera around at the end of this robot, I can just twist it, and I can feed the robot in and out just by moving it up and down. I can also control the speed of this as well, in case I want to do quite precise movements. So that twist and feed mechanism is the way of inserting the robot inside of this turbine. We insert it through the borescope port inside of the turbine, and it eliminates the need for these engineers to use their hands and move it around. It means we have precise control over that. We also have control over the tip. So I'm going to move the tip, I'm going to move it back up, because we're just, say I want to do a scanning movement. There you go, you see the robot just going in, and I can move it so I can look around a bit more precisely. There we go. The light here is because it's a dark environment. We need this light to light up anything that needs to be inspected. And I'm just controlling this robot just with my thumb. It's really, really simple to use. So that is our Cobra inspection robot, long and flexible, much thinner than the other robots that we've presented. I'm going to pass you over to Muhammad, who is going to present another.
Hello, everyone. My name is Muhammad Al-Banna. I'm a PhD student here at the University of Nottingham, and I'm currently working on a project with BT. How can we implement this snake robots in inspecting the infrastructure? Supposedly, there are lots of underground ducts full of all the telecom cables, and from time to time, they need to do inspection and maintenance on these cables. So we had this idea is to attach a snake robot to the tip of the orange cables that they usually do in inspection, so that it would help the orange cable to maneuver between the cables in the underground. And one of the challenging parts in this project is we want to have the snake robot be actuated up to a distance of 50 meters. So in order to test the idea first, we created a mechanical joystick that would control the snake robots attached to the orange cable. And as you can see here, we are using this mechanical joystick to control the snake robots on the orange cable and guide it between the cable. And then we manually push the orange cable between the telecom cables. The advantage of this is because before you were just doing it manually without any real control on the tip, they can sometimes damage the cable, or it would be difficult to maneuver between them. So this is one of the other industrial applications that we are working on. That's all for me, and back with Khalid. Thank you.
Muhammad. And thank you everyone for attending this lab live. And we continue working on snake-like robot in order to improve their design and control. And we improving their design by using like smart design, which need less maintenance and enable different function. Also, we are working on their sensing capability, improving their sensing capability by force sensor, shape sensor, and so on. Also, we working in developing advanced models which enable more accurate control of the snake-like robot in order to achieve high precision positioning for them. And also, we explore snake-like robot in different application apart from the current application like aerospace and nuclear and infrastructure inspection. So now, before closing this session, I would like to thank all of the guys who contribute to this demo. So thank you very much, guys. And now we are happy to have any question from you guys. So the first question is, what is your favorite thing about your job? Oh, okay, this is a very hard question. So okay, I'll start answer this question, and then I'll pass it to Sam and Erwin to share their experience as well. So my job actually includes two parties. The first part is research. The second part is teaching. So what I enjoy in research is basically solving the challenge, solving the problem, which can push the boundary of science in order to improve the life of the human in general. So, for example, by achieving this kind of snake-like robot, we can make the maintenance faster. We can give you like faster travel and easier travel. By developing this kind of robot, we can improve the patient experience during the surgical operation. This is for the first part. Once I learned from my research journey, so I would like to transfer this knowledge to my student, and I would like to transfer for them like the latest experience and knowledge I developed during my research. So this is what I like about my job, basically. And now I'll move it to Sam and Erwin to express their opinion as well.
Thank you. So I've been here about 8 months now, so not so long, but it's been quite a fast learning process. And I think the thing that I enjoyed best is this technology is so young. It's got a long way to mature. So it's valuable to be able to work on a technology just in the early process, and just to watch it evolve. Owen?
Well, very different from Sam. I have been working here for 11 years. Well, indeed, this is a very long journey since we started the research on snake robots. The most enjoyable thing here is we already started to use our academic research to benefit real industry, aerospace, nuclear, and we can see our academic research is very valuable to our society, and this is the most happiness the happiness thing in my job. And also we are growing the next generation of engineers like Sam, so we can keep the UK in the front of robotics research, and this is also things makes me very happy. Okay, I think we all answered this question. Yeah.
So hope this answers the question. This is a medical application, right? So yeah, I think we already start to expand the application of industrial application to a medical application. So yeah, we are working on this direction already.
Also, these devices, these continuum robots, are used in the medical sector, and they're used to replace the catheters. And so they need to be really small. But it doesn't mean that you can't enlarge these technology and use it as prosthetics. So use it to aid people just doing normal, like, human actions.
Next question.
Yeah, you like to go for it. Okay, what has been the biggest challenge you have encountered while doing this research?
Yeah, I think we
can express different opinions.
yes. Well, I will start. So I think here, because we are developing a technology which needs a long journey to mature, so we don't have the biggest challenge. We have the current challenge. So previously we have a challenge on mechanical design, so we need to make the snake robot long enough so it can have enough reach capability, so deep inside the industry environment, and also the snake needs to be stable enough so it can provide enough accuracy for the snakehead to do operations. And currently, because we have very matured system, mechanical design system on Cobra, so we are moving our research focus from mechanical design to control and also a vision system. So this is related to the PhD to Sam. So I will leave Sam to express his opinion.
So my views on the biggest challenge that I've faced so far is probably having to solve something that hasn't been solved before. So I'm looking at how do we know where the robot is inside of this environment? And then how do we use that knowledge in order to control the robot and get it to go where we want to go? This challenge just hasn't been solved before. And just being on the edge of research and actually understanding what I can take from like other areas of research, what other areas of solving these kinematics, and just almost conjoining it and giving my own solution.
Yeah, one of the challenges also we face, especially when we started the journey of the snake-like robot, is that up to now there is no like accurate model of snake-like robot, and this is a challenge which we are trying to solve by developing accurate model for the snake-like robot, which will help us to develop a fully accurate control system of the snake-like robot. Okay, and I think we are at the end of this session. So thank you very much, and we are going to see you in a few minutes.
Okay. Hello, everyone. My name is Xindong. I'm an associate professor on robotics at the Rolls-Royce University Technology Center at the University of Nottingham. Welcome to our live lab show. So at the UTC, our research focuses on the development of snake robots for inspection and maintenance in industry environment. For example, aero engine, aircraft wing, telecom channel, tunnels, and nuclear facilities. So very similar to keyhole surgery for human being, snake robots we developed can be used to reach the defects in industry environment through very small access and then repair them. So in this way, there's no need for disassembling the industry environment and then assemble all the parts back together. So it can reduce the repair time and cost largely. We have involved in this topic for more than 10 years, which is a very long journey. And today we are going to present you 5 different snake robots we developed in our center. And the first one is the grandfather snake robot. So this is a robot consists of multiple sections. This is, well, all the sections are cable driven, and the cable are powered by the motors in the base of the snake. Because the arm is remotely controlled by steel cables, so the arm can be built with a small diameter and a slender structure. And this robot was built 11 years ago. That's why we call it the grandfather of the snake. This was funded by an EU project, and we used this robot for evaluate the performance of this concept and also find out the challenge behind it. After this robot, we build other different robots which has better performance. And I'm going to hand it over to my colleague Khalid for introducing the next robots. Khalid, please.
Okay, thank you, Aaron. My name is Khalid Muhammad. I'm assistant professor in mechatronics at Rolls-Royce University Technology Center. So as Aaron mentioned, so we have a long journey in learning and developing a snake-like robot. And one challenge we identified in the grandfather snake-like robot is that it can be easily twisted around itself because it includes a central backbone. And this prevents this grandfather snake-like robot from applying a large payload at the tip of the snake. So basically, it cannot hold a tool in order to do machining or inspection in confined space. So after that, we have developed this second generation of a snake-like robot, which can hold a larger payload and apply larger force at the tip. The main advantage coming from it is mechanical design, where we replaced the central backbone with a twin joint here. So it makes it very rigid in twisting, and it can, as I said, it can hold a higher load and apply higher force at the tip. So any snake-like robot consists of 2 main parts. The first one is the body of the snake. The second part is the actuation back. The body of the snake consists of different sections. So in this case, we have 8 sections here. So each section is driven by 3 cables. So in total, we have 24 cables coming through the body of the snake. And then all of the cables go to the actuation back, where each cable is attached to individual motor. And then by controlling all of these motors simultaneously, we can control each section individually and simultaneously. So inside this actuation back, also we have all of the electronics, controller, sensors in order to provide the requested motion of the snake-like robot. So also at the tip here, you can see we have a working channel in the snake-like robot, goes through all of the body of the snake and then goes through the actuation back. So we can send any kind of cameras or inspection tool inside the robot, and in order to do the inspection and repair in confined space. So at the end, only we have two cables here to control this robot. One is going to the computer, and the other one is going to the power supply. So the robot in itself, it's very light. It is just 7 kilograms, so it can be carried by a single person. And also it has a ability to be coiled around itself, so it becomes very, very compact. And in this case, it is transportation to the intervention location very easy and convenient. So once we take it to the intervention location, after that we have a control algorithm which allows the robot to be uncoiled automatically and navigate inside a confined space simply by using a joystick, for example. We have demonstrated this snake-like robot in different scenarios. So as you can see in this video, we have demonstrated it in a nuclear environment. So here we have the robot first was coiled, and then start uncoil and navigate inside this tube in order to do inspection and repair. So you can see it is construction is very flexible compared to any kind of industrial robot, so it can navigate easily inside confined space without any problem. Also, it can avoid any kind of obstacles if you have them inside the environment. So as I mentioned, we demonstrated it in several environment to simulate the nuclear sector. So in this one, we have demonstrated it in a glove box. So where you have a very tiny hole, and then the snake navigate from this tiny hole in order to do inspection inside the glove box. So this is a one version of the snake-like robot, which is very long one, around 1 meter. And here we have another version of snake-like robot, which is a very short snake-like robot. So it is basically a few centimeters, as you can see here. And also it is driven by cables through these linear motors. And at the tip here, we have a machining end effector where we can do grinding or machining inside the engine. So the main advantage of this robot is that it does not need a lot of human intervention. So we just need to attach it to the engine, and then a specialized engineer can take control of this one from Derby. So you don't need to send a specialized engineer to the location of intervention. So the next generation of the snake-like robot we have developed here is based on the experience we learned from this robot, where we find that the diameter of this one is a little bit large, so it cannot navigate in a particular parties inside the engine. So we have developed the second generation, which is flare robot, which is 12 millimeter diameter. And now I'm going to handle it back to Erwin to explain about flare robot.
Yeah, so flare system consists of a pair of snake robots for repair of thermal barrier coatings in aero engine combustor. So from the video you can watch now, in this system, the first snake, which is an inspection snake, carries cameras and ignition tools. First enter the combustor and find out where is the defects in the engine, and do evaluation to measure what is the size of the defects, and then to introduce the second snake, which is a repair snake, carries high temperature flame repair tool into the combustor. And after the repair snake reach the defect area, the inspection snake will help the setup of the repair snake. For example, set up the standoff distance from the surface to the snake head. And then the snake will help the repair snake to ignite the flame. And this flame is 3000 degrees C. So it will form a high temperature zone, and which is not very friendly to the fragile electronics in the inspection snake. So the inspection snake will retreat and then come back to monitor the repair snake. And after the repair, the inspection snake will check the repair quality and make a decision whether it needs another loop of repair or the snake can retreat. Okay. If all the repair is qualified, then both the snake will retreat from the engine combustor. Okay, so far all snakes we introduced are around 1 meter long, and the arm of the snake is directly attached to its actuation system. So it requires a large transport box for transport this snake to different industry sites, which is not very friendly to the end users. And recently, we developed a much longer snake, and it is a modular, which is much more friendly for transportation. Okay, and now I'm going to hand it over to Sam for introduce our latest development.
Hi, my name is Samuel Wild. I'm a PhD student here at the University of Nottingham, and I'm focusing on the control of the continuum robots that we have. So as Owen mentioned, these continuum robots, well, this one's called Cobra, and it's much longer and much more flexible than the other robots that we've presented. It's also smaller in diameter, and it's to feed inside of a turbine engine, a turbine. So this robot is made up of 3 active sections. So there's actually one at the base down here, and then there are 2 at the top. So in these active sections, we have four cables which actuate each section. This is what the section looks like. We have individual vertebrae spaced out along the section, and then there's nitinol rods in between these sections to enable flexibility. You can see if I pull on one of these cables here, the backbone of the robot will bend. So it will enable 2 degrees of freedom, or 4 directions. So coming over to this robot, traditionally, when we perform inspection on the inside of the turbine, we will use a borescope, which is a long, flexible optical device that we will push, well, that humans will push and feed inside of this Aero engine and to have a look around. And think about how hard this is going to be, just to move it up and just look around. So our solution is to make a robot that will feed itself in and be able to control the end effector, or the tip of the robot, really precisely. So coming over to the robot itself, we have a modular base. This modular base can be clipped in and out of the computer system really quickly. We have individual cables that I demonstrated before that will control each active section, and then motors that will pull on each cable. So 4 motors will control 1 section. So we have 12 motors. This screen over here is to feed back information to the engineer that's controlling the robot. We can tell all sorts of things like the status of the system, to the angle of the end effector. So you see, we can see the tip, the mid, and the base section. We can see those angles. The way in which we control this robot is using a joystick. It's very simple to use. So if we were to feed the robot inside of the engine, I will just move up on this joystick. And then say I want to feed it back down, I'll move back down. And we can also twist as well inside of her. So look, I can move up and also have a look around just by twisting. If I was to control the active section, I'll just press one button and I'll just move around. So look, I'm going to have a look around just much more precisely. There's a light on the end of this robot because it's going to be a dark environment for the engineers to look around in. And we have a camera on this robot. We're not limited to a camera. As we've demonstrated, we can put different end effectors on these robots so they can perform different processes. So that is the Cobra system for inspection of the Aero engines. I'm now going to pass you over to Muhammad, who's going to talk you through another industrial application.
Hello, everyone. My name is Muhammad Al-Banna. and I'm a PhD student here at the University of Nottingham. Currently, I'm working on a project with BT to adapt snake robots and use it in inspecting the infrastructure. Our main goal is to attach snake robots to the orange cables that they usually do. They usually use to inspect the cables in the underground ducts. What they typically do is they manually push the orange cables that you can see in the pictures here in order to navigate between the cables. What we're gonna do when we add the snake robots to the orange cable is that we add the ability to maneuver between the cables so that we can inspect it better. One of the main challenging parts for us is to increase the length of this system to go up to 50 meters, which, as you have heard before with my colleagues, that currently we are working on 3 meters, 5 meters, 7 meters, and sometimes 1 meters. So we did a demo test to see what is it possible, and it worked. We created a mechanical joystick to control the snake robots at the end of the orange cable to do the inspection. That's all for me. Thank you, and back to Khalid.
Okay, thank you, Muhammad, and thank you everyone for the attention you have on this live. So we continue working on snake-like robot in order to improve their design, modeling, and control in order to achieve a precise motion of the snake-like robot. And before ending this session, I'd like to thank all of the guys who enabled this live demo at our end. Thank you very much, guys. And now we are happy to have any question from you.
So how do cable actuate as a snake, and how many degrees freedom does it have? I think probably this question, Sam, would you like to answer it?
Sure. So for this current snake, which is the Cobra robot, we have 2 active sections. We require 12 individual cables to actuate the snake, and obviously it's 4 cables per section, such that it has a total of 6 degrees of freedom in total.
And for other snake robots have developed, for example, the robot in front of Khalid, it has 24 motors, so it drives 8 sections. So each of the section has 3 cables.
Yeah. So if you look here, this section, for example, is driven by 3 cables. So 1, 2, 3. And after that, these 3 cables go through only through this section, and after that continue to the rest of the body. For the second section here, you have another 3 cables which ends here and then continue to the last to the actuation back. So every section we increase 3 cables. So here's 3, 6, 9, 12, and so on until the end. Here we have 24 cables. And regarding your question on the degree of freedom, so each section includes 2 degrees of freedom. So here in total we have 16 degrees of freedom for this robot, and also we have additional degree of freedom, which is the rotation around it itself. What kind of actuators or motor do you have? Okay, for this robot, normally we have DC motors. So actually, the snakes we have developed here, not necessarily to follow a linear path. So this is just a simple case if you'd like to follow a simple path. But we developed the control algorithm to move along different kind of trajectory. As you have seen, navigating inside the engine is not a linear path. Also, coiling and uncoiling around itself, it is not a linear path. So we have developed algorithms to navigate in different trajectories. So, Sam, do you like to have this question?
Well, I first started developing snake robots 8 months ago. I don't really have much I can comment on this because it's been a learning process. But yeah, I think Owen is better to answer.
Yeah. So, well, actually, we started the research on snake robots. Well, with very limited knowledge on it. So at the beginning, well, as a PhD student, when I started on the research of the snake robot, I was thinking, okay, it is a very easy research. It's just a central flexible backbone and use some cables to drive it. But actually, after I gain more knowledge on this, I found, okay, there are a lot of academic challenges in this field, and also a lot of industry need this technology. So, well, what I wish to know at the beginning is, well, this is a very challenge topic.
So, yeah, I can give more comments. Even for the knowledge, which probably we need now in order to improve these snake-like robots, actually is to learn how the real snake works, basically. So if we learn how the real snake works, how they sense, how they control, I think we can improve or design more mature or more real snake-like robots. So problems in motion planning, optimization, discrete systems, etc. Which problem do you think would be the biggest concern for you? So maybe for the time being, we can say as shape sensing, modeling and control, I think, is the main challenge, which now we are developing algorithms in order to, algorithms and the hardware solution in order to overcome these challenges. Next one, yeah. So okay, I read the question, and if you like to answer it, you can do it. Are there any simple toys that use similar mechanism as snake robots?
Okay.
Well, I'll tell you a story after you answer the question. So
Well, actually, well, in my house, I have a 1-year-old daughter, and there is one toy which is a toy crocodile, so which has a very similar structure with snake robots, which also have a lot of flexible a flexible backbone, and you hold it, and the head of the crocodile can look around. So I think that is the closest toy which is similar to snake robots. I think Khalid, feel free to comment.
I have different story. So I remember after we finished this flare robot, my son at the time, he was 4 or 5 years old, and he all the time asked me about what you are doing in your work. Basically, I'm talking about the snake-like robot, and I bought him at the time a toy of Aeroplane. And what he did, he bring some flexible wire in the house, and he formed it in a kind of snake-like robot, and he started to insert it inside the aeroplane in order to simulate a kind of snake-like robot toy. So this may be Yeah, he's preparing himself to be a researcher of the future. So can we give a chance to Muhammad or Matteo to answer these questions, if you like, guys?
So if you want to use a wireless robot and send it in, first it's going to have all the actuation pack inside the snake robot. So it's going to be big in size. And here we're talking of a snake robot in a diameter less than 2 centimeters. So imagine moving all this actuation pack inside a 2 centimeter diameter. So it's going to be difficult. And if you send a wireless robot, there's a chance that you may lose it there. And then in the end, you will have to dig the ground, take out the underground duct to take your robot. So there's a chance that the things that you wanted to avoid ended up doing it again because you're using wireless robot. That's mainly my answer.
So Matteo, do you like to answer this question?
Well, it depends on the robot and the application. Out of our robots, the one with the highest payload is probably mirror the one that's used for nuclear, which can hold up to 200 grams in standard conditions. We can also increase or decrease this payload by changing the tensioning of the cables and making the robot shorter if needed.
Sam?
So Cobra can move up to about 20, 25 millimeters a second, and that's through the twist and feed mechanism. Same with on the active section on pulling the cables, we can get up to about 20 millimeters a second panning across. How accurate it is a very different question. Currently, the only feedback we have on this robot is the camera. We don't actually understand the shape of this robot. So in order to actually be able to reach more accurate control, we're going to need to develop a system in where we integrate sensors down the snake and feed that data back to a computer or to the control algorithm such that we know where the snake robot is and actually feed it, change the control algorithm. At the moment, we are just using some calculations in the forward kinematics to be able to move the robot. And because of stuff like friction in the cables, it's not perfect. It's not a perfect model. So we need some form of sensor in there to actually understand where the robot is and to improve the accuracy.
Okay, thank you very much, Sam. Thank you, everyone. And thank you very much for your attention. So if you have any interest in the snake-like robot, you can contact us. All of our videos also are available on our YouTube channel, our social media channel, LinkedIn, Twitter, and so on. So please contact us if you are interested in any further information. And thank you very much. And thank you very much for all of our team who enables this demo to be happening. Thank you, guys.